All right. Hello, everyone. Good morning, afternoon, evening, nighttime, whatever time you're watching this. In section 2.4, we're going to be looking at some physical applications of the math we've been doing, the derivatives and stuff. When I say physical, I literally mean like physics. So, for those of you who are in physics, get ready for Physics 2.0. For those of you who are not in physics, don't worry. I'll take my time to make sure you got all the definitions and stuff. For those of you that are in physics, um, I don't want you to skip over this page just because I'm going to change the way we word a couple things. I want you to know the math notation for the things you've seen in physics. So you'll recognize the vocabulary words. Just make sure you identify how we notate them in math class as well. So the first thing that we need, well, and there's a whole list of them here. The first one is displacement. Displacement is change in position. In your physics classes, you've probably notated this with delta x or delta y. I feel a hiccup coming on, and well, anyway, if it comes, it comes. Now in math class, though, typically we designate position with the variable s or with just any generic function like f. So then that would make displacement like delta S or something like that. Or you could just write out the word the displacement is. You might be asking yourself, okay, wait a minute. Isn't that just distance change in position? Okay, displacement has direction associated with it. So say, for example, if you went 5 steps to the right and then 5 steps to the left, over here our displacement would be 0 because you end up back where you started, but the distance would be 10 steps. So that's the difference between the two. Again, it's change in position between, let's just say, two reference points in time, maybe. Okay, then we have velocity. Velocity is basically how quickly is something displacing. It's the rate of change of position. So rate of change, remember, those are our fancy words for slope. So basically velocity is the slope of some graph that represents position. That's pretty nice. Now, of course, if it's a rate, that means we're measuring it over some period of time. What period of time we measured over? That's where our next two come in. We have average velocity and instantaneous velocity. So let's look at average first. Average velocity is where you actually have 2 points and you find the slope between them. So average is always over 2 points, between 2 points. So like I know where I am right now. I know where I am 10 seconds later. Change in position divided by 10 seconds, that would give me my average velocity. Instantaneous velocity goes along with the derivative. That's the slope of the tangent line, or the slope at a single point. There's a bunch of different ways we notate instantaneous velocity. We can use v of t to stand for velocity at a certain time. We could use the s, kind of like we used for position back up here. We could say it's the derivative of s with respect to t. That would be dsdt. Or again, if you had a generic function for position like f or j or g or whatever, then you would just stick a prime on there. Let's see. So kind of like we had distance and displacement, right? We also have speed and velocity. You might be thinking, okay, what's the difference between speed and velocity here? Same thing. Speed does not have any direction associated with it. Velocity does. So we can have a velocity of like -5 miles per hour, but we can't have a negative speed. We would just say the speed is 5 miles per hour. You could also have a direction. You could say it's like velocity is 5 miles per hour west or north or something, and with the speed you would still just say it's 5 miles per hour. Um, I'll remind you of the difference there when it comes up. Or right here, see, I changed this notes page this year. This is why you leave yourself notes on what you change, because I forgot. Here it is right here, Mr. Doolin, big genius, making great videos. So speed, in addition to being unsigned, is just the absolute value. It's really simple. So for velocity, you need slope. For speed, you need the absolute value of the slope. Easy, right? Maybe on its own easy, but I can understand if you're thinking, "Oof, this is a lot of vocab to start off with." It's okay. Might take you a day or two to get used to, but you'll be fine. Okay, we have two more here for you. Acceleration. Acceleration is just how quickly velocity changes. So once again, it's a rate of change, this time of velocity. Rate of change, that's our magic phrase. That means slope. So acceleration is the derivative of velocity. So that's our first one right here. Acceleration is the derivative of velocity. But velocity is the derivative of position, right? So acceleration then is also the second derivative of position, whichever way you want to get there. If you have velocity, derive it once. If you don't, but you have position, you can derive it twice, and that can get you down to acceleration. Once again, like I mentioned before, average means the slope between 2 points. Instantaneous means derivative, so that'd be the slope at 1 point. Most of the time with acceleration, we're using instantaneous, but just wanted to make you aware. You might be asking yourself, what about deceleration? We have acceleration, what about deceleration? Well, there actually is no such thing in math or physics as deceleration. That would just be acceleration in the opposite direction. So deceleration is actually just acceleration in opposite, whoop, scroll over here, direction. So then there will be a lot of times in our class where we'll talk about, hey, is this thing speeding up? Is this thing slowing down? Basically, with this whole direction thing, speeding up, that's going to be when velocity and acceleration are in the same direction. Velocity and accel are same direction. And then slowing down is when they're in opposite directions. Opposite directions. The list does continue on there from there. We don't use the ones past acceleration very often. The next derivative down the line is called jerk. It's the rate of change of acceleration. That would make it the second derivative of velocity, the third derivative of position. If you want to keep going down the list, so I'm just actually just going to make a like kind of a better visual here. So you have position, you have velocity, we have acceleration, we then had jerk, and the way you can just move down this ladder is by deriving, etc. You derive every time. We can actually keep going down this list for a long time. If you're curious, the next ones are like the Rice Krispies. They go snap, crackle, and pop. And well, if that's just not enough for you, the next two are your favorite dance moves. Actually, I probably shouldn't say that. I bet that could get me in trouble. They are the lock and they are the drop. So those are the next two. But like no one ever calculates them out that far. That's ridiculous. But they do exist. My favorite joke that I'm not going to get to use this year because we don't have class is I tell people to not talk when I'm talking because that makes them a real third derivative. But alas, here we are. Okay, especially again, I do recognize not everyone's in physics. A lot of people are taking it next year. If they weren't this year, that's fine. Um, this is not like a once-off, hey, here's these things, okay, know them forever. We're going to practice with them a whole bunch. In fact, the next, what we have left today is two sample problems, and I'm just going to remind you every step of the way. If this stuff, seems trivial to you, please work ahead, pause the video, go for it, just check your answers, that's totally fine. So I'm going to give you two different types of examples here. The first example is where I'm just going to give us an equation. We're going to do a whole bunch of derivatives, stuff like that. And then in the second example, I'm going to give you a graph instead. So two different ways of us looking at the same style thing. So for our first example, we have a function which gives us position. So we have something, I've just called it a particle. Ooh, a particle. A particle moves in such a way that its position is given by this function. Then we have a whole bunch of jobs. We'll just run down the list here. Our first one is find instantaneous velocity at time t. So it's not even at a specific point in time. Well, instantaneous velocity, that is the derivative of the position function with respect to time. So you could say that's ds dt, or if you prefer the prime notation, then you would say that it's s prime of t. This is too big. I need to make this smaller. So whichever way you want to write that. And then you have some options here. We just need to come up with that function. So we can either product rule this, or we can multiply this out and then derive it using the power rule. Doesn't matter. How about let's product rule it, df(g)(f)(d)(g). So let's see, s prime of t would be df. So let's see, that would be, bring the 2 down, d minus 2 to the first power, and g plus f dg, the derivative of the second thing over here, the t minus 4, that would just be 1. So that's not really anything. And then normally I I say, hey, you know what? You don't have to simplify here, but I'm just thinking to myself, this is a polynomial. Like, look, we're gonna have to derive it again for acceleration. We're gonna have to do stuff with it. Let's let's just simplify it to make it easier to work with. So let's just multiply it out real quick. Um, let's see, we're gonna have, what would that be? That'd be like t squared minus 8t plus 8, and then all that's gonna be multiplied by 2 plus t squared minus 4t plus 4. So then distribute the 2, put everything together. Let's see, there's going to be 3 of them, t squareds minus 16 minus 4. Hold up. Haha, there's the mistake. Boom, that's not 8, that's 6. I was trying to, yeah, it doesn't matter. Okay, so then that'd be 12 of them minus 4 would be minus 16t, and then 16, 20. So there is our instantaneous velocity. You could say it's v of t, or you could say it's s prime of t, or ds dt, all that works. Okay, boom. And again, I'm only simplifying because I know we're going to have to use it to do other stuff. Otherwise, I totally would have left it this way, and that would have been fine. Okay, our next job is to find the acceleration of the particle. Okay, well, here we go. Now that I have a simple velocity function, my derivative is going to be really easy. This is now just a power rule. I got to bring the exponents down. So 3 times 2 gives you 6, and then 1 times 16 gives you 16, and that's it. If we hadn't done this simplification, we would have had to product rule this, and then we would have had to power rule that, and then maybe we would think about simplifying. So I like to think that our work paid off right away. Okay, our next question then is, when is the particle at rest? So for those of you not in physics, at rest is kind of a magic phrase. That means uh, when is the velocity equal to 0? And specifically, this would be instantaneous velocity equal to 0. Well, we have a velocity function, so let's set that bad boy equal to 0. 3t squared minus 16t plus 20. Sometimes you can solve these by hand. Sometimes you quadratic formula, graphing calculator, that sort of thing. I think this one's factorable, right? It'd be 3t and I think it's minus 10 minus 2. Yes, yes. Okay. So then we can solve there. We get positive 10 thirds and then positive 2. If we had context like seconds or minutes, I would label here, but we don't. So we can leave them without units. That is totally fine. You only have to answer with context when you're given context. Find the displacement of the particle from t equals 2 to t equals 5. Remember, displacement is change in position. It's always going to be, just like in science class, final minus initial. So this would be the position at time 5 minus the position at time 2, which, I mean, the original thing, we can plug in 5 into that and 2 into that pretty easily. That'd be like 5 minus 2 is 3, 3 squared is 9, 9 times 1 is 9. Plug in 2, you get 0. And once again, if I had units, I would give context. I would say 9 feet, 9 miles, 9 meters, whatever, but I don't. So it's okay to just leave it as 9. Average velocity, remember that is the rate of change between 2 points. And the giveaway here is I had to give you the 2 points, right? These are 2 points in time. This is t equals 2, t equals 5. So let's see, average velocity then, that is the slope of the position function between those 2 points. So that'd be like s of 5 minus s of 2, y1, y2 minus y1, right? Over x2 minus x1, which, hey, look, we already did the numerator there. That was the displacement in the previous part. So we found the displacement was 9. It takes place over a total of 3 seconds. That means our average velocity would be 3. And again, if we had units, I'd say miles per hour, meters per second, feet per fortnight, I don't know. But we don't, so it's okay to just leave it as 3. Finally, our last thing is to find both velocity and speed of the particle at t equals 4. Well, the velocity at 4 would be plug 4 into that instantaneous function, which was that quadratic up here, right? So you plug 4 into that. 16 times 3, 16 times 4, so we're going to be left over with minus 16 plus 20. Looks like it comes out as a nice even 4. And then speed, remember speed is the magnitude of the velocity. So in this case, they're the same. The only time they're going to be different is if one of them's negative. Okay, so that's kind of a functiony example. Now I'm going to give you a graphical example on the next page. This graph is a velocity graph. So it shows velocity at any given time. So I immediately I see, okay, it's got a positive velocity for a while, it's got a negative velocity for a while, then it's got some more positive. Typically, the positive direction in calculus means things like forward, right, up, north, east, etc. Directions like that. The negative direction typically means back, well, the opposite of all those. So backwards, left, down, south, west, etc. So like you'll see in these questions, I'm asking, okay, in this question I asked forward, backwards, speed up, slow down, blah, 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 blah. The forwards and backwards, forward, give me the positive stuff, negative, give me the backwards stuff. Now remember, this is a velocity graph. So this is telling us not only how fast is it moving, but which way it's moving. So let's break it down. Let's answer the question. So A asks a lot of, or two things, forward and backwards. So this thing moves forward whenever it has a positive velocity, and that would be in the upper region here of the graph. So that looks like that happens from 0 seconds up to 1 second. And then it resumes moving forward in the 5th second, and it goes all the way until the 8th second. And that's when the graph stops. Whoops. There we go. Now here's the thing. Okay, now this is jumping forwards a little bit in the next chapter, which we'll talk about in August, I guess, at this point with how crazy 2020's been. There is a theorem that basically says slope is never like, or increasing, decreasing is never defined at a single point. So the textbook will actually argue that you could also correctly answer this question by saying from 0 to 1 excluded, because the velocity is 0 there. So how can you argue it's moving forward? And then again, at actual 5 seconds, it's an intercept. So how can it's not moving there? But it would resume again, open interval immediately after 5. It would go until 8. And basically, as a consequence of that, it's a corollary to a theorem. Both of these would be acceptable answers. So whichever makes more sense to you, that's the one I want you to use. Then backwards would be this region down here, just the domain in which the y values are negative. So you would either say from 1 to 5, or you could say from 1 to 5 with open endpoints. Again, it doesn't matter. The two are both correct. My request to you is just be consistent. So like if you're giving me this one here with the brackets, give me brackets both times. Or if you're using the parentheses one, give me parentheses both times. Because like it'd be weird to do it one way and not the other, I think. Okay, took care of A. B is when is the particle speeding up, when is the particle slowing down? So I'm going to clear off my graph here. Remember, speeding up, we said, was 2 pages ago, speeding up is when velocity and acceleration are in the same direction. So that would either be both positive or both negative. Either is fine. So let's take a look at our graph here. Actually, I'm going to do some, let's label. I'm going to get a different color to label it. So over here, all the negative slopes I'm going to do in red. So here's the negative slope, here's a negative slope. And then the positive slopes I'm going to do in blue. So here's a positive slope, here's a positive slope. And then that black line is where the slope is 0. So for speeding up, I need, come on, zoom in. There we go, too far. So I need, well, let me write out speed up. I need a positive velocity and positive acceleration, which would be slope on this graph, or I need negative velocity and negative acceleration, which again, that's the slope. So let's look for, is the slope positive and the velocity positive on this graph anywhere? Yes, right here. This region that I'm now doing in green is an area where we have positive velocity values and a positive slope. So that would be one area where it's speeding up. That would be from 5 to 7. Again, you could do brackets or parentheses here. And there's also a region where we have negative velocity and negative slope. That would be right over here. So I'm also going to have to link that to from 1 to 2 seconds. And again, brackets or parentheses, don't care, just be consistent. For slowing down, so slow down, that's when the two don't match. So wait, I probably shouldn't use red because I already used red on the graph. Let's do purple. So slowing down, that'd be when I have a positive for one thing and a negative for the other. So like here's where the graph is positive, but negatively sloped. Here's where the graph is negative, but positively sloped. Here's another region where the graph is positive, but negatively sloped. So we have a whole bunch of areas where this thing is slowing down. That would be from 0 to 1, and then again from 4 to 5, and then again from 7 to 8 seconds. Ooh, I just thought of another good way to describe speeding up and slowing down. Slowing down, this one's easy. Velocity is getting closer to 0. And then speeding up, that would be velocity is getting farther away from 0. Vel is getting farther from 0. Hopefully that makes sense in the context with our graph over here. So I know this is like really messy, so I'm going to clear off all the colors now. Here's the regions where the velocity is getting closer to 0 from left to right. Those were the regions where it was slowing down. Here are the regions where the velocity is getting farther away from 0. Those are the regions where I argued it was speeding up. What we got next? When is the particle's acceleration positive, negative, and 0? Okay, so for C. Remember, acceleration, that's the slope of the velocity. So the slope of the velocity is positive. Let's see, so let's say positive on, looks like that would just be from 4 up to 7. That was these two areas, right? We have a negative slope from 0 to 2, and again from 7 to 8. 0 to 2, and then again from 7 to 8. And then we have 0 slope for this flat region here. It looks like 2 to 4. And once again, like I've said 4 or 5 times already on this page, you can give me brackets or parentheses. That is fine. as long as you're consistent. Okay, let's see, reverse direction for our next one. Well, that would be when does velocity change sign? So I'm sorry, guys, I ran out of room. Sometimes it's hard to write like small on the computer here. So for D, that would be where does velocity change sign? And that seems to happen at t equals, looks like t equals 1 and t equals 5. And then finally for part E, when is this body moving at a constant speed? Again, that would be 0 acceleration. We already figured that out. That is from 2 to 4 minutes, seconds, whatever. I didn't give you units. But again, that would be whereas, here I'll just say because v of t is constant, slope equals 0. Whew. All right. Hey guys, I know that was a long video. I appreciate you sticking in there. Please, 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 please let me know what questions you have. I'm by the computer basically all day from 9 to 3. I can email you back real quick, or we can jump on the microphones during office hours or whatever. Um, but yeah, that's it for today. Thanks for your time.